Okay, let's start. So I believe we have homework 90 today, right? So hopefully that went okay. We're going to do a lot with functions today. I have a lot to get through. Let's see. And that's with me skipping a lot of the proofs. We'll do a few proofs, but we're going to skip a lot of them because they're too long to write out. But your textbook will have most of the proofs that we're going to be talking about. So let's actually recap from where we were last time. We were talking about cardinalities. It's kind of a measure of the number of things that your set contains. And we talked about what it means to be having the same cardinality or numerically equivalent. Which roughly means they have the same number of things. So if you have A, B, have the same cardinality numerically equivalent, you would write the size of A equals the size of B. And what did that mean?
You can find a bijection.
You can find a bijection. There exists some function from A such that f is a bijection. So it needs to be one-to-one and onto. And we kind of did that example about, the students and the chairs, and that's how we know we have the same number of both sets. So this is the definition of what it means to be numerically equivalent. This will work for finite sets as well as infinite sets. It gives us a way of counting without actually counting, because a lot of times we will be dealing with things that have infinite sizes, but we still want to be able to compare these sizes. So the functions help us with that. I introduced what it means to be denumerable. So what does it mean to say A is finite?
Vector list.
Huh?
Vector list.
Sure, it does mean you can list them, but there's something else.
The cardinality equals n.
The cardinality is some natural number, right? So perhaps with union 0. So you can have the empty set as cardinality 0, or you can have a set with 5 elements, or so on. Denumerable means to say A is denumerable. What does that mean?
Countably infinite.
Countably infinite? Define it.
It's infinite. It's an infinite set. There's a bijection between A and N.
There's a function from n to a such that f is a bijection. So we call this A's denumerable means countably infinite. We also spoke about what countable means. What does countable mean? It means you're finite or denumerable. So you're one of these two. You're either a finite set or you're countably infinite. Countably infinite, by the way, or let's just say countable in general, by the way, also means listable. Meaning you can write down a list of all the elements, or you can show that such a list could theoretically be written down. So this means we can theoretically, at least, list all the elements. So of course, if it's finite, this can be done. You might have a long way to go to write it down. If it's infinite, it can still be done. All you have to do is show that I can write this in a list in such a way that I will never miss anyone. If I could keep writing for it infinitely long, I would eventually write everyone down, right? So how this works is you can use the function f. So remember, f goes from n to a bijection. For example, if I look at f, it will look like this. It's just going to be it's just going to be a relation, a set of ordered pairs, where 1 goes to one element of a, 2 will go to another element of a, 3 will go to another element of a, and so on, where the ai are in a. So we can think of a as just a list of things. So I can talk about, here's the first guy, the second guy, the third guy, the fourth guy. I can write them in a list, and I'd be able to do this and exhaust the list. Infinite set that is not countable is called, surprisingly, uncountable. Math people are very creative when it comes to choosing names for things. So, and by the way, countable sort of means listable. So that kind of tells you there is a kind of infinity that's so large that we can't actually write things down in a list. There are too many of them to actually list, which might seem strange at the moment, but we'll actually show that that's not the case today for the real numbers. That was going to be our first example of an uncountable set. We'll actually show for an integral of the real numbers, and then by extension show that it's true for the real numbers as well. So, countable infinite means there's a bijection from the natural numbers to the set. As a consequence of this, it means you can actually write out the elements of the set in a list. The list might be infinitely long, but as long as you can show I can write down these things in a list by some method that will never miss anyone, this is doable. You would have something that's countably infinite. Right? If you don't have something fulfilling that criteria, we call it uncountable. So, by the end of today's class, I want to show that uncountable things are larger than countable things by a lot. I will also want to show that you cannot list uncountable things, because any list that you try to come up with will be incomplete. You will never be able to come up with a strategy to list things so that you never miss anything, because there are just too many. Every time you write down a list, there's going to be someone missing, an infinite amount of people missing. Okay, so let's actually do some examples here. The integers is denumerable. The set of all integers is a countably infinite set, meaning, basically what I'm saying here is that the size of the integers is actually equal to the size of the natural numbers, which might be counterintuitive since it seems like this guy only has half of those guys, but no, they actually have the same number of bits. Proof. Define f to be according to. So here's how I'm going to do the function f. Here's my n. I'm listing the n terms along the top here. That's going to be my domain. And I'm going to tell you what each thing is mapping to. So 1, my function will output 0 when I plug in 1. Plug in 2, it will output 1. Plug in 3, it will output -1. Plug in 4, it will output 2. Plug in 5, it will output -2. And in this way, I can actually list all the integers. And by this pattern, I would never actually miss anyone. Now, this requires, or this is a bijection. Clearly it's one-to-one and onto because it will never miss anyone. Some remarks though. Finding a nice formula. So we don't want to think of functions just in terms of formulas. May be very difficult. It is okay at this point to show some rule via a strategy to list all elements. Here's our mark. A function that does this. By the way, for this one, it's not terribly. Actually, there's actually a formula for this. It's actually the formula that would give you that. But in general, writing down a nice formula is not usually going to be in the cards. It's going to be very difficult, especially when you get with start dealing with more complicated sets. So it's okay to actually describe the rule via some sort of diagram. It'll be clear how your inputs get to respective outputs. And it'll be clear, it should be clear that it's one-to-one, because you have each guy mapped into one thing. And it'll be onto, because clearly every integer will appear at some point in this list. So very nice if you can find a function to describe what you're talking about. Sometimes that's very difficult. It's okay to describe it by other means. Just make sure it is a rule that is a function. It's well defined, it's clearly understood, and it has the property of being able to list everything without missing anyone. So it turns out there are the same number of integers as there are natural numbers. Let's keep going. Here's something we're going to, here's another example. Define Kn to be the set of Kn such that n is a natural number, and K to be the set of all Kn such that K is an integer. Then it turns out that this guy is the same as that guy. It's also the same as the naturals. Via for the first one, 1, 2, 3, 4, 5. Look. Let's map this to k times 1, and k times 2, and k times 2, and k times 4. So this shows that Kn is actually equal to the size of n, and similarly, if I go 1, 2, 3, 4, 5, 6, 7, map this to 0, map this to k times 1, map this to k times minus 1, map this to k times 2, map this to k times minus 2, shows now, we can get a lot of things for free out of those two, because those can describe, for example, things that we're already familiar with. Like multiples, any multiples of a number is basically what I'm trying to say. So I can have something like, if k is 2, this is the set of what?
Okay.
Set of even integers. So, example here, if k equals 2, k is just the even integers. So I can look at all multiples of 2, it's the same as everyone. It's the same size as the entire set. All multiples of 3 is the same, all multiples of 4 is the same. I can take out any multiples, I'll still have an infinite number of them, and I'll have the same amount as if I was looking at the entire set in the first place. Here's an important theorem. We're not going to prove it, but your book does a proof of it. Using the well-ordered principle, and just by choosing the minimum, it can construct a denumerable set. So here, any infinite subset of a denumerable set is denumerable. So this will cover all of these examples. If you have any denumerable set, any infinite subset of that set must also be denumerable. You can prove this using the well-ordered principle. We're going to skip proof done in text. Not terribly complicated, but it's a very long thing to write out, and I just don't want to bother. So it basically starts out by assuming that there's some well-ordered set, assuming that there's some denumerable set S with S1, S2, S3, S4, and then it creates a subset of S that's also infinite. So let's say it picks S2 and it renames it B1, then it picks S5, renames it B2, and so on. And basically it shows that you can create a list of elements, and basically it just starts by looking at the minimum value of the subscripts that you can get to throw in this. That's where the well-ordered principle comes in. But yeah, if you have a denumerable set, something you can write in a list, then any infinite subset of that, you would be able to write in a list just by renaming the subsets, the subscripts. You do that by the well-ordered principle. So the argument for that, to write it down properly, is it's kind of really long, so I don't want to go into it. But we'll use this fact pretty soon. It's something you should know. It's actually an important thing. So I would never actually ask you to prove it, but there are definitely going to be problems on like tests and things like that, where you'll need to know that. Definitely you'll need to know that for homework as well. So that's one of the really important theorems. Let's look at something else. Another example, I think this is also done in the book. If A and B are denumerable, then A cross B is denumerable. So the set of all coordinates where the elements in the first and second coordinate come from denumerable sets, that will be denumerable. Here's a nice little trick to do with that. All we just need to do is describe some rule that can list all the elements, and we will just show that we can do this in such a way that we don't miss anyone. So how we sort of do that is via a grid. So let's list all the elements of A, and go A1, A2, A3, A4, A5, A6. You can list all the elements of B, B1, B2, B3, B4, B5, B6. So those are all the A's, those are all the B's. And now I'm going to actually take the cross of them. What that just means I'm creating coordinates not lining up here, but we'll see. A1, A3, A2, A3, 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 A4, A3, A5, A3, A6. Okay. And basically what I can do now is I can define a rule that will actually start to list all these guys. I will write the list this way. So clearly, this will be my first element. Let's call it C1. This is the second, C2, C3, C4, C5, C6, and so on and so forth. So I can actually create a new list. So I can think of A cross B as the set containing the elements C1, C2, C3, C4. Clearly I will never miss anyone by doing this strategy. And so I take F1, 2, 3, 4, 5. 1 maps to C1, 2 maps to C2, 3 maps to C3, 4 maps to C4, 5 maps to C5, and so on. Is a bijection. We can extend this. If A1, A2, all the way up to AN are enumerable, then A1 cross A2 cross A3 cross AN is enumerable. You can use that, show that via induction. It's also the case that if you have a countably infinite number of countably infinite sets, and you take all their cross, all the Cartesian products, that's also going to be enumerable. You need a little bit more than induction for that. Yeah, countably infinite. Sorry. Yeah.
Sorry, there's something on the line, sorry, you can do a regular V induction.
Yeah, in induction is how you do it. You know it's true for 2, and clearly it's true for 1, because A cross with A by itself is enumerable. Clearly it works for 2, and you just create a large coordinate by thinking of the first n minus 1 coordinates as one coordinate, and then the last coordinate as the other guy. And then you can do a similar idea here. And so that goes by induction. Here's another theorem. The set of positive rationals is enumerable. Again, you can do a very similar thing. Just do a grid. So then 1, 2, 3, 4, 5. But in the first line, divide it 1 by 1. Then go 1, 2, 3, 4, 5. Second line, divide it 1 by 2. Divided 1 by 3. And so on. You'll be able to list every rational number this way, potentially, in theory, and just choose a function that does the same thing. So that's the first guy, the second, the third, the fourth. See, this guy was chosen before, so we skip over him. reduces things in this manner and skips over any element that was already chosen. Right? So you can reduce them all and just take your rule to go through the list in this manner, but skip any one that's been chosen before. Surely this, you'll be able to list a bunch of guys here, Q1, Q2, Q3, Q4. Skip that guy, this is your Q5, that's your Q6, your Q7, your Q8, and so on. And so we can write this Q1, Q2, Q3. So that's the numerable. Set of all positive rationals is denumerable. From that, we can prove that the set of all rational numbers is also denumerable. Q is denumerable. Basically, proof. The function this goes to 0, that goes to Q1, this goes to minus Q1, that goes to Q2, this goes to minus Q2, that goes to Q3, this goes to minus Q3, is a bijection. So Q is denumerable, right? All these sets have the same number of things in them. So the natural numbers, the integers, all integers of a certain multiple, the positive rationals, all the rationals, they're all the same size. They're all infinite, but they're all the same size. They're all the same category. We're still all in the countable state. We haven't broken into the uncountable yet. So, but that should give you some sort of an appreciation how difficult it is to break out of infinity. You can take infinite subsets, create Cartesian products, divide infinite number of things, and we'll talk about a lot more examples as well in the next book. But you'll always remain countably infinite by doing this. So let's talk about the uncountables. In order to talk about that, I want to talk about decimal expansions for a little bit. Note there are 4 kinds of decimal expansions. One, these guys are the finite decimal expansions. So for example, 1 is a finite decimal expansion. You can look at a half, which is 0.5, is a finite decimal expansion. 0.4 equals 0.75. You can express the entire number as a decimal, and you can do that in a finite number of ways, using a finite number of digits. 2, you can have infinite repeating patterns. So that's something like what? 1/3, which is just 0.3, 3, 3, 3, repeats infinitely. And, you can also, you can have these of several digits as well. You might have done examples like that. 7/11 is 0.636363. Right? So this is just 0.63 bar. And you can you can create decimal expansions like this that have repeat any length of digits forever that you can choose. And that will actually always be able to write as a fraction via, you can use series, geometric series, to rewrite these things. So, there's two infinite repeating patterns. The third kind, those with two different but equal expansions. Example, 1 is equal to 0.99999, but I can also write it as 1.000, or I can think of 0.5, it's the same as 0.49999 forever. These are actually exactly equal to each other, even though they might look different. And this is again something you can prove using geometric series. You probably did that in Cal 3. Here's the fourth kind, the non-repeating. So example, pi. That's an infinitely non-repeating decimal. It does not have a pattern. It is not finite, and there's no pattern at any point that actually repeats. So those are all the possible decimal expansions. By the way, the first three are all rational. Types 1, 2, 3 are exactly the elements of Q. Now, type 4 lives in the real numbers minus Q for the irrationals. I might write this as I, even though that's not official. So these guys here are the elements of Q, all these possible kinds of decimal expansions up to the first three, which means there are a countable number of them, right? So I can actually write down a list of all such decimal expansions such that I don't miss anyone. And essentially that would be me writing down Q. The fourth kind though, the non-repeating ones, those are a different animal altogether. So let's actually talk about that. What are we doing now? Let's look at the interval 0, 1. Here. 0, 1 is uncountable. This theorem basically says that if you look at all the real numbers between 0 and 1, you have an infinite number of them, and you will not be able to write them down in a list. In fact, the size is different from the size of the natural numbers, is another way of saying that. So I'll do this proof because it's kind of important. Use a very famous argument called Cantor's diagonal argument. George Cantor is the guy who did a lot of the foundations for set theory, and he really was a pioneer in all this stuff. So first, we're going to ignore the repeats. That means I'm going to randomly choose a guy like here, right? I'm going to ignore these guys. So if several decimal expansions exist, choose the one that ends in all zeros. Because I want to make sure I'm not double listing anyone. So that's the first step. Make sure we're not choosing things that we don't need to be choosing and over-listing things. So now, here's what we're going to do. Assume to the contrary. So we're going to pretend we can list these things. 0, 1 is countable. That means the interval 0, 1, I can write it as a list of things. A1, A2, A3, A4. Write each element thus like this. So A1, I'm just randomly choosing a guy in this list. As the first guy is 0. 2, A21, A22, A23, A24, A25, A3, A31, A32, A33, A34, A35, A34. Where the A, I, J are elements of 0 to 9, right? So these are just digits. So I'm writing out the decimal expansions of the numbers that are between 0 and 1. So it's going to be 0 point something. And I'm listing all of these guys. And I'm assuming I can list them. And I can keep going, right? So I can do this A1, A2, A3, A4, list them all. So I'm assuming it's countable. There's an infinite number of them for sure. Let's pretend that there's a countably infinite number of them. I can have a bijection from the natural numbers to this set, such that natural number 1 maps to this, 2 maps to that, 3 maps to that, 4 maps to that, 5 maps to that, and it would be a bijection. Here's where Cantor's diagonalization argument comes from. Basically, no matter how you write down this list, you will always miss someone. That's going to be the argument. It's not listed. You can't actually write them down on a list. Once you put 2 real numbers, write them down on a list, there's an infinite number of real numbers in between them. You'll never be able to list them all. So here's what we actually do. Define a new number. Call it B. Where the BI are digits. Right? So I'm going to define a new decimal expansion that lives in 0, 1. Notice that this guy will be an element of 0, 1. By the following. I'm going to tell you what BI should be equal to. Set it to be 2 if AII is not 2. And set it to be 3 if AII is 2. That's going to be how I'm going to create a decimal expansion.
Where you pick 2 and 3?
Come again?
Where you pick the number 2 and 3?
Arbitrary. A lot of people use 0 and 1, a lot of people use 5 and you can, it's gonna work no matter what. In other words, notice who I'm looking at, the AI's eyes, these are the guys on the diagonal, so that's why it's called the diagonal argument. So I'm looking at these guys here, whatever their values are. And I'm going to apply this function. I'm going to say, if the number is not 2, change it to 2. If it is 2, change it to 3. Okay. So, let's do an example. A1, A2, A3, A4. So B would be equal to. Okay, so give me some random decimals. It doesn't even matter. 1, 2, 3, 4, 5, forever. Okay, 0.2279113, 0.110238, 0.555555. Okay. So those are the guys. So here's what B is going to do. It's going to look at the diagonal elements. This guy, this guy, this guy, this guy, and go down. And so what would B be in this case? What's the first element? 2. Right, so if it's not 2, write 2. Okay? Go to the second element. It is 2, so instead I'm going to write 3. Third element is not 2, I'm going to write 2. This element is not 2, I'm going to write 2, and so on and so forth. Right? So I'm creating a new decimal expansion based on that criteria. For each AI, look at the digit in the ith position after the decimal place and change it according to this. Now, B differs from every Aij because it has a different value in the ith position. So B is not in the list that you just wrote down. So you pretend that there are countably many, you could list all of them. It turns out, no matter which list you write, I can create someone that's not in your list. So every time you can write down a list of real numbers in between 0 and 1, you will never be able to complete this list. Even if you assume you would be able to write things down forever, you would literally never be able to write everyone down. That's how infinite the interval 0 to 1 is. Right? It's more infinite than the integers. You can theoretically, okay, if you give you infinite amount of time, you could write down all the integers. You can't do that with the numbers between 0 and 1, the real numbers. Every time you write down any list, if you assume you have the whole list, we can create someone not in your list. And then if you put this guy in the list, I can create someone not in the list, right? So if I put this guy in the first position, then I create a new B, because that was 2, change that to 3, and now it's different from everyone in the list, right? So every list you can create, there's a guy not in your list. You cannot list them, even assuming you can list things forever. So the interval 0, 1 is uncountable. Start to see what that means in a little bit. But basically we're going to show that this means it's bigger. Uncountables are bigger than countables. technically to make such a broad statement, you need accent controls to work. Let's actually move. So this is a very famous argument, that's why I wanted to show you. It's kind of like one of those arguments about proving that the square root of 2 is irrational, right? Proving that the numbers between 0 and 1 are uncountable via Cantor's diagonalization argument is a very famous kind of proof. So this was using Cantor's diagonalization. So if you ever see that mentioned anywhere, it's talking about this. The numbers can change here. The point is you're changing things on the diagonal to be different from what they currently are. Doing that will create a new number not in the list. So you'll never be able to complete this list, not even in theory. Here's something we can do. Here's another theory. Suppose B is a subset of A. If B is uncountable, then A is uncountable. If you have an uncountable subset, you yourself must be uncountable as well. Proof here is not that bad. Who thinks they can do it? If you contain an uncountable set, you must be uncountable.
Assume B is uncountable.
Assume.
Oh,
yes.
sorry. Yeah, assume B is uncountable.
Yeah. B is uncountable. Assume B is uncountable. Okay.
Then for any element B in B, B is in A.
Sure. And where do you go for that?
Can you prove my contradiction?
Okay.
Oh, then assume A is.
So assume B is uncountable, but A is countable. Then what can you say?
Then A is listable. I mean, the elements, then all of A's elements appear can be written in a list.
Yeah. So that would mean what?
Meaning, and then since B is a subset of A, meaning that every element in B can appear in the list, but B is uncountable.
Right. So, what you can do, a nicer way to say that is to just invoke the theorem we have before. However, by the previous theorem. But what you said is fine. Don't know, this is the previous theorem. Infinite subsets of countable sets are countable. And the reason is because of what you said. If I can write all of things in a list, then if every element in there is an element in here, ultimately all of those guys will appear in the list. But we're saying uncountable means all the things cannot appear in the list. So this would mean B is enumerable. And that's the contradiction. Another thing. set of real numbers is uncountable. Proof.
Could we just say that 0 to 1 is a subset of that, and if that's uncountable, then R is uncountable?
0 to 1 is a subset of R, and 0 to 1 is uncountable. This means R is uncountable. Part of the above theorem. So the real numbers contains an uncountable set, it must therefore be uncountable. A lot of other theorems here to get through. Okay, let's just go through it. Every two denumerable sets are numerically equivalent. Let A, B be any two denumerable sets, then they are of the same size. So any two sets that are countable, they will have the same size. What do you think about 0, 1? Has the same number of things as the real numbers or less?
I mean, I want to say less.
I want to say less. Yeah, you want to say less. Yeah, okay, let's continue. We'll eventually get there. Proof. How would you go with this?
Could you use something similar where you had two numerable sets, like when you were using the natural numbers and the integers, and then just map any A to any B? Like
Okay.
A1 to A.
Like A1 to B1, A2 to B2. Let's show this. That will be the idea, I think. But let's actually write that down a little more crisp. So proof. A is denumerable. So we can actually find that function. So there exists f from n to a, which is a bijection. Similarly, there exists g from n to b, which is a bijection. So this is what it means to be denumerable. So we'll assume that we can find such a function. We might not necessarily know what they are, but they would exist if they're denumerable. We would be able to write in a list and just map 1 to the first element, 2 to the second element, 3 to the third element, and so on and so forth. Okay, can you figure out a function that goes from A to B? That's a bijection.
Well, I have a question on that. So, the way I did it was could I list all of A and then all of B and then just without mentioning all that first?
You mean to say, choose,
Like A being denumerable means you can put it in a list, right? So
yeah, so you can list A1, A2, A3, A4, and B1, B2, B3, B4. And then just take F to be the mapping from this to that.
yeah, but my question was like, would it be equivalent to say that if I can list the elements of A, then do I have to write that? Like, that's equivalent to that, right?
Yeah, so you could say, assume A is denumerable. This means we can list all its elements and write A as the set A1, A2, A3, da. Similarly, we can write B as the set B1, comma B2, comma B2,
Okay.
then clearly the function f described by this mapping would be a bijection. So yes, that does work to say that.
Okay.
I'm going to something a little bit more elegant here. We can actually construct a bijective function from A to B, given that we have two bijective functions like that. How do you do it? Yeah?
Could you create a, I was gonna say composite function, but
Okay. How would you do that?
could you use G of F inverse?
Then F inverse would go from A to N and is also a bijection. Then, if you look at G of F, this will be going from A. So F takes A to N, then G takes N to B. So this goes from A to B.
Isn't it G of F inverse?
So then G of F itself. So the idea here is the following. Here's the set N, here's the set A, here's the set B. F went from N to A, right? That's your F. It's a bijection. So I can go the other way using F inverse. That would also be a bijection because we proved it. And then use G to take those elements to B. So then if I compose G with F inverse, it goes all the way from here to all the way there. Is a bijection.
So it should be G of F inverse.
G of F inverse, yes. Is a bijection from A. So any two countable sets have the same size. So once you know a set is countable, it will have the same number of things as the natural numbers, it will also have the same number of things as every other countable sets. So not only is the integers equivalent to the natural numbers, but you can think of them as numerically equivalent to the rationals. You can cut out the middleman. You don't have to evoke the natural numbers all the time, which might be useful. Another thing that we can do. If A is countable and B is uncountable, then the cardinalities cannot be equal. There is no countable set that can be numerically equivalent to an uncountable set. Here is assumed to the contrary. Assume to the contrary that A equals B, then there exists a function from A to B that is bijective. But that means B is countable. That's a contradiction. Let's see. So ultimately, we're learning all the differences between the countables and the uncountable sets. They can never be numerically equivalent, and here is another theorem that Nicholas is going to want to say is not true, but it is going to be true. the interval AB, the size of that is the size of all the real numbers. Where AB is any subset of R, that's an interval. So any two real numbers, I don't care how close together they are, the amount of numbers between those two numbers is the same as the amount of numbers in the entire real line. And of course it gets even weirder. The amount of numbers in that is the same as the amount of numbers in the entire real line, which is the same as the amount of numbers in the entire 2D plane, which is the same as the number of points in the entire 3D space. Like all sizes Rn are the same size. Rn is all equal to R. It's going to be true. I believe, is that a homework? This is actually a homework problem. So you guys can have fun doing that. Let's do some specific examples though. So let's actually look at, say, the 0-1 case. So example 0-1, the size of that is the size of R, meaning they have the same number of things in both of these. How can you show that the size of one is equal to the size of the other?
Show that there's a bijective function.
Show that there's a bijective function. Okay? Give me a bijective function.
Isn't the function some kind of like weird?
There are many things. Basically, you just want to have a function that the domain is between 0 and 1, that it hits all numbers from negative infinity to infinity. So there are tons of functions. Something like a tangent would be like, I think, a nice one to use. So you can do a shifted tangent. If you remember your pre-calc, you would know how to shrink the interval to be of length 1 and then shift it. And I think f of x equals, if you take the tangent of pi, so the period would be pi over pi, which is 1, and then I shift that to be a half, so that the center here is going to be a half. Is a bijection from 0, 1 to all of R. You can verify that. There are many such functions. Your book gave several examples. Here's another one. So let's call this F1. F2 from 0 to 1 to R given by f of x equals 1 minus 2x over x squared minus x. So here they made the asymptotes to be 0 and 1, so that gives you these lines, and then they made sure that the x-intercept is a half, and so on. That's another example. I think that's similar to the book example, might not be the exact one. Here's another example. F3. Let's go from -1 to 1 to all of R by this guy. F of x equals x over 1 minus absolute value of x. This is a bijection. Of course, when I say it's a bijection, we have to verify that. You can say F4. In F4, I can go from, I'm going to do a function from 0, 1 that goes to -1, 1 by f of x equals 2x minus 1. That's a bijection. Of course, you can say they're both equivalent to R numerically, then they have to be equivalent to each other numerically. But here's a specific function that will actually do that for you. There are other functions. Okay, so with these two examples, what I could do is, notice that if I took F3 composed with F4 inverse, that will be a function, another function from -1 to R. Right, using the same kind of trick we used before. Which is, like I said, it wasn't wrong in the uncountable case, but I wanted to give you the proof using function, because when it comes to real numbers, you can't use lists. You have to know how to like manipulate functions. So what you can do is, for the homework, you can think of a way to go from 0, 1 and map to that equal. That would be the easiest one, and then just use a composition. That's one way to do it, but you can actually derive functions in general. Where is another? I have a bunch of examples here. I don't know if I should write them all down. I'll say that for later. I can use those for another fact. Let's look now to comparing cardinalities. So I introduced the countables and the uncountables. Let's start to compare things together. It's useful to know about power sets as well. A non-empty, B any set. Then the power set of A will be numerically equivalent to the set 2 raised to the A. Remember this guy. This is the set of all functions from A to the set 0, 1. Remember that was our definition for 2 today. We're then going to show that the size of a power set is always strictly greater than the size of the set itself. And that's going to help us do some comparisons where we can know not only when things are equal, but when something is strictly greater than. That's going to come in useful. So when something is strictly greater than or less than, and in the last section we're going to talk about if you combine the two, less than or equal to, greater than or equal to, then they must be equal. Proof. Let's define a function. G. Let's go from the power set of A to the set 2 to the A by G of S equals F sub S, that is the indicator function. i.e. F of S is equal to, for each individual element, it's equal to 1 if your element is in the set, it's equal to 0 if your element is not in the set, for all x in the subset you're looking at. So let me actually give you an example here of what I'm doing. So basically, this is, remember how we decided that the size of the power set was actually 2 to the n for n elements, and basically the argument that we did was, just look at each element, either it's in there or it's not, and we sort of counted this way. That's basically what I'm trying to do. I'm setting up a function to decide whether something is in the set or not. The output will be 1 if it's in the set, it will be 0 if it's not in the set. Okay? And this will ultimately, we're going to show, this will exhaust all the functions in 2 to the A in a 1-to-1 manner. So let's actually do a concrete example so you can see this in the two-element set. Okay? What is the P of A?
The empty set,
The empty set,
set containing
the set containing A,
A, set containing
the set containing B, and A itself. Right? So these are all the subsets. These are the S's. Right? And I'm going to take them one at a time. So let's say my S is equal to the empty set. Right? So F sub S is really just F sub the empty set. Now what does that function do? It's going to look at the element A and B, and it's going to decide, is A in this subset or not, right? Is A in the empty set? The answer is no, so it outputs 0. Is B in the empty set? The answer is no, output is 0, right? And that is one possible function that goes from AB to the set to A, right? Then I can look at the other subset, the subset containing A. So now my Fs is going to be F sub the subset of A. So I'm going to look at A and B and decide, are they in the subset? Is A in the subset? The answer is yes, so it outputs 1. Is B in the subset? No, output 0. If my S is the set B, then my Fs is the set F sub the set of B. So is A in the subset? No. Is B in the subset? Yes. Then I can take the final subset, AB. My Fs in this case would be F of the subset of AB. And if I look at, is A in there? Yes. Is B in there? Yes. Right. Now, I've exhausted all the subsets. You would also notice that I've exhausted all possible functions from the set AB to the set 0, 1. They will always be the same number of things, right? And so I'm setting up a function to basically count that. Okay. So I'm going for G is going from the set of all subsets to this set, where G of a subset is just going to be this function, right? That actually does that. So in other words, this I can think of as this guy here is G of the empty set, gives me that. G of the set containing A gives me that. G of the set containing B gives me that. G of the set containing A and B gives me that, right? So when I plug in this subset, that's the output. Plug in this subset, this function is the output. And I'm claiming that these are actually always this. This will create a bijection, is what I want to say. We show G is a bijection. We need to show G is a one-to-one, and we need to show it's onto. Assume G of one subset is equal to G of some other subset, where S and T are subsets of A. This means the functions, their outputs must agree for any value x that you pick. That would mean that Fs of x equals 1 if and only if Ft of x equals 1. And that would mean that x is an element of S if and only if x is an element of T. So if it's in one, it's in the other. This means S is a subset of T and T is a subset of S, which means S is actually equal to T. Let's do onto. let's prove that every function will be mapped. Use onto. Let X be any subset. Let S be any element of the power set. My output was a function. Okay. So let F be any element of 2 to the A. Define B subset of A by, I'm going to let B equals the set of all X in A such that this function f of X is 1. Is my same f here. Then by definition, g of b is going to be f sub b, but f is the indicator function. It outputs 1 whenever an element is in B, but I constructed B to be all the elements such that f is 1. So that is actually equal to the given function. So no matter who you pick, just pick the subset that has outputs 1 for every element in that set, and that gives you the guy in the domain that maps to it. So you're basically going to take the element in the power set such that for all x in here, the second coordinate is 1, and for any x not in there, the second coordinate is 0. Choose that guy, and that's going to be the guy. I mean, what we've said so far is already suggestive of this fact, but I want to build up to the point where we can say for sure that the size of a countable set is smaller than the size of an uncountable set. By a lot. And I'm also going to want to prove that the size of a power set is always bigger than the size of the set itself. So if you're thinking that the real numbers are huge, and you would be right, you might want to think, is there anything bigger than the real numbers? The answer is yes. But let's jump into the gun a bit. Before we move on to the facts like that, let's do some remarks. End after this. 4 sets A, B. If there exists f from A to B such that f is 1 to 1, an injective function from A to B, we say the size of A is less than or equal to the size of B. You can connect everyone in A to someone in B, but you're not sure if there's anyone left over. So if you don't have the onto criteria, you can say B can be exactly the same as A, or it could have more stuff potentially. If A is less than B, and at the same time you can show there is no onto function from A to B, then we say A is strictly less than B. size of A would be strictly less than B in this case. I can connect everyone in A to people in B, but B will have things left over after making this connection. We say A has smaller cardinality in this case. That's defining when one cardinality is smaller than another. Another thing you want to know, it's more notational. The size of n, I don't know how to write this, but it's a Hebrew letter called Aleph Null. That's what I write it by hand. But it's a fancy N with boldface and it has subscript 0. This is Aleph Null, Aleph Not. Basically, this is the first infinity. It's the smallest infinity we know about. The size of R, we call that C, which stands for the continuum. So it's like the real line, there are no breaks in it. We call it the continuum, and we call that C. We have 2 more minutes. There's something called the continuum hypothesis, proposed by George Cantor himself. It says there is no set such that its cardinality is strictly between n and c. It's a hypothesis, we don't know if it's true. Things get worse. A mathematician named Gödel proved that you cannot prove it's not true. And then another mathematician, I believe it was Cohen, proved that you can't prove that it is true. So this is a hypothesis that with our current set of axioms that we know about in set theory, we can't prove it's true and we can't prove it's false either. So it's just kind of this thing we assume. These are the 2 smallest infinities there are. There's the infinity of the natural numbers, there's the infinity of the real numbers, there's no infinity in between. There are infinities that are bigger though, there are many infinities that are bigger. And those are the guys we'll talk about later, as well as the Schroeder-Bernstein theorem. We'll stop there, leave your homeworks. I'm sure if you die in the fire, leave the homeworks. And we'll pick up tomorrow.